We have talked about many different logical systems in this module, and we've talked about how a logic works syntactically and to some extent semantically. When we talk about the syntax of a logic, we mean rules acting on symbols. They transform one string of symbols into another. And we have talked to a limited extent about what those symbols mean in certain contexts. So specifically in the context of mathematics, this is quite easy to do because the meaning of those symbols is effectively another bunch of symbols. If we define mathematical concepts like sets and numbers, and we say symbols mean sets and numbers, those sets and numbers themselves can be represented or interpreted as other strings of symbols. The number 5 could be represented by 5 dots in a row or 5 cars in a row. So doing logic about these artificial entities, like mathematical entities, seems relatively easy. You have a very well-defined structure that you want your model theory to be talking about. But ultimately, especially in computer science, more so than in mathematics, we want our logic to refer to stuff in the real world, the actual world in which we live. And for most of us, this isn't the world of atoms and electrons and superstrings. This is the world of chairs and tables and coffee cups, the macroscopic objects. And I'm putting objects very much in quotation marks at this point. As humans, we appear to live in a world full of these macroscopic objects which have properties such as color and weight, and they interact with one another, they move over time, and we want to have logics that can reason about how those objects will behave. Now, if I park my car in this location at this time, then I will get a parking ticket. That's the kind of thing we would like an AI system, or even just a database, to be able to do. So in order to make logic talk about the real world, we need to have a structure. We need a model theory for what this real world is supposed to be. And this takes us into the domain of what is called ontology. That ont is some really ancient word fragment meaning existence or being, and ology, as in any subject, is deriving from logic. It's the study of, in this case, the study of existence itself. This sounds very grand. Okay, it's less grand than you think it's going to be. We're really studying models of existence. We're really studying how we can write down and represent stuff in the world, rather than claiming that the world actually really, in big quotes, is in this way. You could have a theory that the world is made out of atoms or superstrings or quantum fields or cheese, and all your experiments will show you that, and then one day you take the red pill and find out you've been living in a computer simulation the whole time, and the real world is actually made out of patterns on silicon chips. So we're not really going to say anything here about what the actual real world is made of, but we're going to talk about how we perceive the world and how we can represent it as human beings. And that, I think, is sufficient for the representations that we put into a computer. So you might want to quantify this, right? The theory of what exists in human perception. It all sounds rather less grand. And when you study ontology, it's the most fundamental form of knowledge and study that it is possible to undertake, because everything else you study is dependent upon it. If you study physics, for example, you are going to come up with theories such as this. Here is a theory of physics. It says electrons are objects which have charge and mass. Okay, probably most people still believe that. Actually, real physicists don't. It gets even more complicated. But at a high school level, you might be happy to accept this. Electrons are objects which have charge and mass. What does this sentence actually mean? This sentence depends on you already having a theory of objects and having a theory of properties, right? An electron is this thing called an object, and thing is very much in quotation marks at this point because we haven't defined what a thing is. An electron is an object, and an object has to have other things called properties, and charge and mass are two of those properties. So you very rapidly get into word soup, trying to use everyday words like thing. So we are going to deliberately avoid using the word thing, because thing is an everyday English term. It has a lot of ideas and meanings associated with it, and we don't want all that baggage to go in here. When you study medicine, you deliberately throw out English terms like the black stuff, and you deliberately use a Latin term such as substantia nigra, which means the black stuff. But because it's in Latin, you can tell that it has a formal definition. So we're going to do something similar. We're going to chuck out the word thing, and we're going to use some jargon to deliberately be clear what we're talking about. So rather than talk about things, we are going to talk about entities. And this is a definition. You can see it is written in italics. That means it's a definition. So an entity exists. Okay? That's the definition of an entity. And notice I didn't use the word thing. I didn't say an entity is a thing which exists. I just said entities exist, because that's what an entity is. So what ultimately exists, at least in our perception, it appears to be things such as objects and properties. In order for you to talk about what is there, you will usually talk about some objects, and you will say that they have some properties. So ontology is the study of how to set this up, and computationally this means how do we define languages, how do we define databases, how do we define data structures for use in AI and NLP and on the semantic web that can represent pieces of human knowledge in a way similar to how we do it. So ontology is going to study questions like, what is an object? And in computer science, how are we going to represent that? What is the data structure we're going to use to build an object? What does it need to contain? What does it need to represent? Now, what is an object so that an electron can be one? What is a property so that charge can be one? What does it mean for an object to have a property? You can have the property of charge if you're an electron. You could have the property of redness if you are a car. What about the property of ownership? This car belongs to John. And you might have a feeling that this is a different kind of thing or different kind of entity to a property. Somehow the redness of the car seems to belong inside the car. It's a property of the car itself, whereas the owner of the car, it may be something you can say about the car that it's owned by John, but you couldn't really look down a microscope at the car and see that John is its owner. But you couldn't look down a microscope at John either to see that John owns the car. So you might question exactly what these properties are going to be and what it means for an object to have one. And are there other entities as well as objects and properties? And any suggestions without looking at the bottom of the slide? Let's go to a different slide so you can't cheat. Any suggestions for what other kinds of entities we might want to have, as well as objects and properties.
Like, properties are nice, and the problem is there's some ontologies which try and make like everything an object and a property. So we can say, oh, well, these two objects have a relationship between them. And we say, okay, well, that might be a different entity that's separate from an object and a property. Yeah. But you can also say, oh, okay, well, that's because they share a property which relates to one another. That's I don't know. It depends on how you want to construct your ontology, I guess.
Yeah. So if you've ever tried to program in a language like Java, which really enforces this view of the world, in Java, everything is an object or a property of an object, and you end up coming up with these ridiculous class names in Java. They're very long names for objects that, often for objects that do something. If your robot needs to issue parking tickets, you don't just have a class robot and a class parking ticket. You'll end up having this other object called a robotic parking ticket issuer, and then another thing called a robotic parking ticket issuer logging device. Often you'll see this shoehorning of verbs into nouns. Everything gets turned into an object in Java. So yeah, you mentioned relations as well, right? If John is James's brother, where does that fact belong? Is it a property of John, or is it a property of James? It's a relationship between them, and it doesn't seem to sit naturally inside either one. So you can hack this. If you're writing in C++, you'll often just have a field for, I don't know, list of brothers in both of them, and you'll have a link each way. But you're really trying to represent something that exists outside of those two objects and which connects them together into a relationship. Good. And any other entities? Is there anything you've ever struggled to express in these object-oriented languages in particular? When do you feel that the object view of the world starts to fray a little? Okay, so I do a lot of programming about space and time. Right? When I work with robotics, a robot is a physical object, and it exists at a point in space and a point in time, along with all the other physical objects. And the concept of space can be very difficult to express. So you will find, for example, in databases, when you start doing very heavy work with spatial information, you have to put in extensions to your database. You have to move to what are called GIS, Geographic Information System databases. So you'll find that there are extensions of SQL that give you new commands and new concepts to express space and the existence of things in space. And if you want to ask a question like how many cars are in this city at this time, you're not just talking about numbers anymore. You're talking about points, assuming cars are points, points inside a region, a 2D region defined as a city. And the normal mechanics of SQL don't really allow you to express that very easily. But if you move to a spatial database, it has much clearer concepts of what is a region of space and what does it mean for something to be inside something else or overlapping with something else. And similar for time. The time is another dimension. You can say, tell me all the events that took place inside a window of time. Negatives are often difficult to express. You may be used to a bell ringing at 9 o'clock every day, and then one day the bell does not ring. And even if you express the ringing of the bell in your representation every day, the fact that it is missing on Thursday is very hard to express. The missing sound of a bell appears to be an entity to many people. The missing sound of the bell is more noticeable than the sound of the bell when you've got used to it. And so you might want to talk about the lack of something. There used to be a lack of computer science on our computer science degree, and we have filled the lack with this module called Logic and Computation. But when we discussed that lack, we were using the noun. There is this lack, and the lack is a thing. It's an entity, but it isn't a physical thing. It's the absence of something. Okay, so in the olden days, people used to study this before they did logic. Okay, you used to study the trivium, and you would go to grammar school, and grammar meant ontology, linguistics, syntax, and metaphysics. And then you would go to university and you would study logic and rhetoric. We've done it the other way around because logic now seems like the easier subject, and ontology isn't always needed to do logic. When you do logic that is about mathematics or purely about symbol systems, the MIU system doesn't have an ontology because it's a purely symbolic system. And we can study logic and meta-logic very nicely without needing ontology. So for us, we're studying ontology at the end because it's something we can add to logic if we want to make it point at the real world rather than the other worlds of syntax and symbols and abstract constructions. Many people today think that grammar just means syntax. This was part of the study of grammar. If you study how languages are created, how you combine verbs and nouns, and how you link ontological ideas together to make more complex structures, you need a syntax to put them together. But the real point of grammar is to study the basic stuff that exists in the first place. Metaphysics, by the way, is sometimes taken as synonymous with ontology. Arguably, metaphysics is what you have just after ontology. It's once you've got your basic objects and properties and relations, it's about what should the basic classes be in the physical world, or even the non-physical world, building on that ontology. Once you know what an object is and a property is, are you going to make your world out of atoms or gods and spirits or processes or thoughts and consciousness and so on? So we're not going to do that part of metaphysics. We're only doing the ontological part. So we're really talking about stuff like this, right? We can have this logical term, mortal Socrates. This has got two tokens in it, mortal and Socrates. We intend Socrates to be an object. We intend mortal to be a property. And what does it mean to have an object and a property, and for the object to have that property? So that all sounds very grand. Let's bring it down to Earth, computational Earth. Let's talk about when we actually need an ontology. So this is what I did in my Easter holidays. I have been enjoying hacking in C Natural for the first time, and I've been using C Natural to build a little game engine called Natch, which is basically a C Natural knockoff of Scratch, which is a wonderful educational programming language. So the idea of an ontology at this level is that there are certain aspects of the worlds that we wish to represent in a large class of possible programs we might write, in this case 2D sprite-based games. All these games have a bunch of things in common. They all have the same underlying ontology. There's the same set of stuff that is going to behave in similar ways. And so rather than writing every one of these games from scratch, we are first going to define that ontology. We're going to say what is a 2D video game, what are the basic entities in it, how do they interact with each other, and then that gives us a level of middleware, effectively, which means that each of these games can then be written in about half an hour, because you've already abstracted that basic ontology away. So we've done Space Invaders and a platformer and a fighting game, Asteroids, little brawling game. You can see how they're evolved from one another, right? It's pretty easy to turn a brawler into a fighter, or turn Space Invaders into Asteroids. So when you think at the level of ontology, this is more abstract than just designing a class hierarchy in a programming language. An ontology is something that could be ported between languages or systems. So if you've ever worked with databases and object-oriented programming, or any kind of logic, knowledge-based system, you will often need to move knowledge from one of those systems to another. And if they're all speaking the same ontology, then it's quite easy to do. So an ontology could be instantiated in a class hierarchy sometimes, or it could be instantiated in a database schema. But it's the more fundamental grouping of what exists, and then it's a secondary problem to figure out how to instantiate it in those systems. So, what is the ontology of 2D sprite-based video games? Anyone who's written a simple game will end up coming up with something like this. There are a bunch of game objects, and these are not the same thing as the objects in your object-oriented programming language. These are objects that are in the world of the game. So, your Street Fighter character is in the game, right? Your data structure maintaining the high score table is not in the game. We're talking about what is actually being represented in the world that is being modeled here. So game object, often this appears as a subclass of object if your language starts with a general object. You have to make a distinction between things that are purely computational and data structures and things that are doing representational work. They're standing for something in the real world. Yeah, so a game object could be the car, it could be a particular coin, it could be a particular Space Invader. We often put numbers on the end to show that we mean an instance, right? So if I just wrote coin, that's ambiguous because it could be the class coin or it could be an instance of coin. If I write coin 12, this is the 12th coin that's been instantiated. So what can game objects do? Right, they almost always have an appearance. So in Scratch and Natch, that's called a costume. They must have a location. We're talking about a model of a physical world here that has 2D space, and a game object must exist somewhere in that space in order to exist at all. Similarly, it must have a shape and a size. So together, these concepts are called the extension of the object. They're what define the region of space, possibly time, space and time, that the object is occupying. And in particular, in most cases, the extensions of two objects are not allowed to overlap. If two objects try to occupy the same piece of space-time, then they will collide and other things will happen. So these seem pretty clear. These are going to get built into the basic game ontology. What about mass and velocity? Many 2D games will need these. In the real physical world, as far as we know, everything has to have a mass and a velocity as well as an extension. But you can kind of imagine that there are games where these are not needed. Not every game has a physics engine. You always need the extension, but you don't always need these physical properties as well. Now, these are spatial properties. They're just describing static extension. These are physical properties which are used in calculating dynamics according to Newton's theory of physics. And sometimes these game objects will acquire other properties as well. The health of your character, how many lives, how strong is the character, what is the value of the gold coin. Some objects are more valuable than others. They will score more points and so on. So you can kind of see there's a hierarchy. There's properties that are really essential to being a game object. There are properties that are quite common in game objects, and there are properties that are completely arbitrary that depend on the particular game that you happen to be making. So you can define your game object with as much of this stuff as you like. You decide where your ontology is going to stop and where you leave it to the user to extend it. Not everything needs a strength, for example, but everything needs a location. But the game object is not the only thing to exist. You also have this concept of a game class. You want your object to be an instance of a class in most cases. So let's keep this concrete. Here's my little Space Invaders game. There's a bunch of, how many? Probably about 15 instantiated Space Invaders. But also in this game, there is the class Space Invader. So the class is an entity. The class exists as well as the objects instantiating the class. Now, unlike the objects, the class doesn't exist in space and time. It doesn't have a particular location, shape, or size. It contains the information that stuff will be needed by any object instantiating the class, but it doesn't actually occupy space. You can't look into the world of my game and say there is Space Invader, the class. You can only ever see instances of the class. So a game class is somehow going to describe the form of a group or a collection of objects. It's going to describe the things they have in common. Or possibly a class is the group of objects. It's the collection of all possible Space Invaders in some theories. In other theories, it's not the collection, it is the abstract form of Space Invader, the abstract shape and structure of what a Space Invader is. So consider the class of red things. One way to view this is that it is the collection of all actual red things. It's a class that includes your red car and my red pencil and every other red thing we can find. It's like a set. It's the class of all red things. The other way to view a class is that it's this abstract form that just describes what it means to be a red thing. And this fairly quickly gets tricky. The classes are entities. A class exists. We can talk about the class Space Invader, but they don't exist in space and time. So we appear to have discovered a non-physical entity, possibly for the first time. We now require the existence of something that doesn't have spatial extension. So on the other side of this, you have the properties. What is a property in the class of 2D video games? So in most systems, most programming languages, databases, a property has 3 components, and you will represent these in a table if you write a compiler. If you write a good compiler, at least. So most properties will have a name and a type and a value. So I'm writing a game, it's got a cat in it. That cat has a property called age. The name of the property is age. The type of the property is either int or float, and the value might be 3 or 3.5. You might have integer energy or float x location. Values of some properties are these primitive types like ints and floats. Values of other properties can actually be other objects. So this whole thing is now recursive. You have the concept of a class. An object is an instance of the class. The class defines a property. The object gets an instance of the property. And now the content of the value of that property is now another object, and the whole thing will recur. Now, in other cases, the value is just the name of another object. And this matters a lot in a language like C++, because you're at the level of memory, you're asking, am I going to carry all the information about this sub-object around with me, or am I just going to carry its name and the object itself can live somewhere else? At the level of ontology, you're asking, is that other object actually a part of this object, or is it outside the object and my property is just referencing it somewhere else? Is my arm actually part of me, or is the thing that I have just a link to that arm? And this is all the stuff that you take for granted if you've only learned to program in one, usually object-oriented language. There are other ways that languages can be created, and the people who define the language that you're using have made certain choices, certain decisions about these big ideas. So just a little bit of philosophical background. I'm going to try and keep this to a minimum, but it's important to understand which world we are talking about when we do ontology. So a basic, possibly the basic concept in philosophy is the difference between the noumenal world and the phenomenal world. Okay, the phenomenal world is the world that you experience every day, and it consists of these macroscopic objects like a house and a person and the sun and the sky and the ground. And look, in your perception, the sky is above the ground, so there's nothing here. This is how children always draw the sky, because the sky is above the ground, right? The sky isn't here. You don't color this in blue because there isn't sky there. The sky is above the ground. There's nothing in between the sky and the ground. So this is the world that we experience every day, and which we usually want to model in our programs and talk about in our languages. We would usually like to believe that there is some other world which also exists called the noumenal world, which is normally defined as what exists if there is no one there to look at it. Okay, this phenomenal world only exists while you are alive, and when you die, it all goes away. There's no one to perceive this house anymore. Whereas you would like to believe that when you die, there might not be an object called house anymore, but this house, you would like it to, in big quotes, really be made up of little things called noumena. And noumena may be atoms or superstrings or cheese or your favorite theory of what the world is made out of. The brains of evil computer programs that have taken over the world and enslaved humanity. But you would like to believe that there is something objective that exists even when you are not there, and that these noumena somehow give rise to the presence of the phenomena, the house. So the house is a single thing. This is an object in your perception, whereas the noumena are usually considered to be small and independent things, and somehow processes here give rise to the creation of this phenomenal world. Sometimes people try and imagine the noumenal world inside of their phenomenal world. So what you have here is a model of the noumenal world, which I call the pseudo-noumenal model. So this is if you're a physicist and you're thinking about superstrings, you can imagine the world being made out of particular little kinds of blobs, and you hope that that is a good match to the structure of what is actually there, but you're never quite sure because you might be wrong. It might turn out that we're all just living inside the matrix and there aren't any superstring at all. That's why it's called pseudo-noumenal. Pseudo means not quite, but the best we can do at the time. So when you read ontology by philosophers, there's this duality. Sometimes they're talking about this world and sometimes they're talking about this world. Okay, there are philosophers who think that the actual noumenal world has a certain structure, that can be expressed, for example, in first order logic. Some people think the noumenal world has objects and properties and relations. I have absolutely no idea what is in the noumenal world, and I'm not going to make any claims about what is or isn't in it. I'm only interested in this world, and I'm much more confident that this world has objects and properties and relations, because those are the things that I experience every day. So this distinction goes back a long way. There's an ancient Vedic story called The Snake and the Rope, where you're looking at a rope and you think it's a snake. You perceive the rope as a snake because it's short and thin and wriggly. And so the snake exists in your phenomenal world as a snake. But in the noumenal world, there's something more like a rope. You find it in Western philosophy, in Plato's cave. This is the one where you're captured and tied up in a cave, and you can only see the shadows on the cave wall, and that is your perception. And unbeknownst to you, there are all these real-world 3D things moving around, creating the shadows, which is the noumenal world. Your phenomenon only has the shadows. And more recently, this was the inspiration for The Matrix and a bunch of other sci-fi stories where you're living in a virtual world of some kind. So, in computer science, we generally want to work in this world. We generally want to build systems that are models of our phenomenal world and which can make inferences about them. Elliot.
Yeah, it's probably a bit of a weird question, but does the existence of the pseudo-nominal model suggest an existence of a pseudo-phenomenal world? Or is that a pseudo-phenomenal model?
Yeah, okay. This is definitely off topic. I refer you to my past life as a philosopher on some of this.
Okay.
Yeah, okay. So look, you might. It's the last lecture of the season, though, right?
Okay,
you
sorry.
might have a phenomenal world. You might have a phenomenal world which includes other people in it. Okay, and your model of the world includes not only those people but also their phenomenal worlds. So look, this guy's got a little phenomenal world with a house and the sun in it as well, coming out of his head. Yeah, so now you've got a model of their phenomenal world as well. And you can keep going, right? Maybe they've got a little pseudo-nominal world as well. So now you've got a pseudo-phenomenal, pseudo-noumenal world or something in there. Yeah.
Yeah, I thought it'd be something like that where it could just keep on going on forever. Okay.
Yeah, that's where it gets really interesting. It's often those worlds that give you the motivation to believe in the noumenal world in the first place, by the way, because some philosophers have argued that the phenomenal world is all there is. This is a position called solipsism. You're the only person that exists, and everything else is just a percept in your world. But the problem with that is you'll very quickly run into these other people, and you'll hear them talking about their phenomenal worlds, and it becomes very difficult to account for why all this stuff is here. And so people usually they end up agreeing that there must be this underlying noumenal world in order for it to generate your world and the worlds of the other people, and to make them all consistent with one another as the simplest explanation. Okay. Good, but totally off topic. Okay, so the philosophers will use ontology to talk about that stuff. We won't. We will apply ontology in computer science for practical purposes. An ontology enables a logic to reason about part of the real world. It is supposed to give you a representation of the real world, and then your logic can act upon that representation in the well-defined ways that we've seen logics can do. And this usually requires a division into what is called upper and lower ontologies, which will form the later divisions of this lecture. So an upper ontology is this very abstract top-level theory of the basic entities. The theory of what is an object, what is a property, what is a relation, what is a spatial temporal interval, what is an event, what is a whole or an absence of something. So upper ontology doesn't change very much. Ideally, we would only ever have one theory of upper ontology, and everyone would agree to use it. So this concept will show up, for example, when you are designing a logic, when you're designing an interpretation, you're designing first order logic, and you say, what is this structure where you say mortal Socrates? So what are these symbols actually going to refer to? This is an object. This is a predicate, actually. Remember, a predicate is anything you say about something. We haven't actually defined a property yet. I've been using them a little bit too interchangeably. So yeah, substances and predicates. So when you design this type of ontology, you may be preparing to do some AI, you may be preparing to do some verification. I use verification here in the easier sense than AI. Verification in this case means you've been given a logical argument and you're going to check that it works. Whereas when we talk about AI, we're talking about rhetoric. How do we actually create the logical argument in the first place? This comes up in the design of languages. So object-oriented programming in its current form enforces a very specific upper ontology on the world. Everything is an object, which is an instance of a class, and classes have properties, and objects have instantiated properties coming from those classes. And that's, in pure object-oriented programming, that's all there is. Oh, functions. What is a function? Is a function a property of an object, or is that something else? Discuss. It comes up when we design databases, not particular databases, but the database programs themselves. When we define SQL or when we define the relational model. And there's a very famous conflict between these called the object relational impedance mismatch. Things that can be expressed in an object-oriented program will not always carry over easily to a relational database and vice versa. And so hilarity ensues when you try to mix these ontologies together. For far too long now, people have been talking about creating the semantic web rather than actually creating it. The semantic web is supposed to embed ontology into XML, and so a web document, not even a web page anymore, a web document is just going to be this expression of entities in an ontology, and those expressions will sit on servers all around the world linking to each other like web pages do, but you'll be able to just put in a query, show me all the cheapest hotels in Canada next week, and the internet will go off and use ontology and logic to find the answer to your query based on those semantic representations. A less ambitious version of that is just getting a few different data sets to talk to each other. If two scientists go and run an experiment, collecting pictures of stinging nettles for robotics, you need them to express the results of their experiments in the same ontology to be compatible with each other. One of them might have a variable called length, and the other one has a variable called width. In data science, you'll often get this. You'll just receive a database with this thing called width in it, and you have no idea what it's the width of, or what units it's measured in, or anything, and it's completely useless unless everyone has first agreed on the underlying ontology, where if there's an object called stinging nettle, and stinging nettle has property width that is the maximum width of a leaf observed anywhere on the plant, or however you choose to define it. So upper ontology is just getting this shared ontological language and structure together to define what stuff is going to be made out of. Lower ontology is defining what particular stuff you have in your domain. So you'll see much more activity here because there's more work to be done. Every domain needs its own ontology. Upper ontology only needs to be done once, so it evolves over thousands of years. Lower ontologies get created every day in science. So, for example, the ontology of my 2D video game engine, that is a lower ontology. I'm defining what particular kinds of object exist, like a space invader or a spaceship or an asteroid. You'll find lower ontologies in web design. We have this document object model that describes what is a web page, what are the the things inside of a web page. And then you will find attempts at semantic web, usually based on XML, where some aspects of this lofty ambition have been realized. In theory, every website selling books is supposed to have an XML ontology describing a book, which enables you to search not only their website but everyone else's website to find who's selling it cheaper than on the site that you originally logged into. Yeah, what could go wrong with that? The open ontological web without any walled gardens. When we go to science, you'll see the best developed forms of this. Biology in particular has evolved to the point where no human being can know all of biology anymore. And so you have to represent biological knowledge in computational ontologies. Now, there are millions, billions of facts probably that can be and are expressed in these formal ontologies now, such as the gene ontology for genetics. Music has recently gone through this process. We now have a standard-ish ontology for representing music called Music XML. And this isn't just an XML format. The XML is just one way of instantiating it. You could instantiate the same ontology in an object-oriented language or in a relational database, but it defines what is a note. A note is an object that has a pitch and a duration and so on. And you've probably all seen these knowledge graphs appearing in sites like Wikipedia. Now, when you pull up a Wikipedia page, there's often a panel in the top right that has pulled out the salient facts as formal data structures. If you look up a famous composer, it'll pull out their year of birth and the name of their famous symphony and so on as data fields. So you need ontologies, lower level ontologies to describe these. What is a composer? We're going to define the ontology of composers, and then we're going to go around and extract those formal ontological data sets from every text article. And ideally, they go together. A lower ontology should build on an upper ontology. You first agree on what your basic entities are. Are we having objects? Are we having relations? Are we having events? Are we having space and time? And then you define your lower ontology as an extension of the upper ontology. Should we have 2 tea breaks today? I'm feeling
you would like to.
Yeah. Let's come back at 3:10 and we'll try and have 2 tea breaks.